if we now consider a light ray traveling from a dense to a rare medium, meaning that the light ray is incident onto a medium having a lower refractive index, in other words, eta 1 is greater than eta 2, then for a sufficiently small angle of incidence, the light ray is refracted into medium 2 accompanied by a weak reflected ray in medium 1. If now the angle of incidence is slowly increased, so will the angle of refraction. So the refracted ray will be more bent away from the normal as the angle of incidence is gradually increased. Eventually, we will strike an angle of incidence at which the angle of refraction is 90 degrees. In other words, the light ray will exit along the boundary between the two media. So here I'm showing the incident ray at a particular angle such that the angle of refraction is 90 degrees. It exits along the boundary between the two media. And we call this angle of incidence the critical angle C. We give it the symbol C. Again, a weak reflected ray appears in medium 1. Now, this angle is called the critical angle because if it is exceeded, in other words, if we keep on increasing the angle of incidence such that it is greater than the critical angle, then the light ray will be totally reflected back into medium 1. And no light will pass into medium 2. And this is shown in this diagram here. So here we're showing that now the angle of incidence exceeds the critical angle. No light is transmitted, which means that no light passes into medium 2, and all light is reflected back in medium 1. And it obeys the laws of reflection such that the angle of incidence is equal to the angle of reflection. The critical angle is hence defined as that angle of incidence for light traveling from a dense to a rare medium for which the angle of refraction is 90 degrees. In fact, it also marks the onset for total internal reflection. So, as we're saying, total internal reflection is that phenomenon observed when light is incident onto a rare medium at an angle of incidence which exceeds the critical angle. No light will be transmitted into the rare medium, but all light will be reflected back inside the dense medium. And here we have a summary of the conditions that must be met to attain total internal reflection. These include, first, that the light ray must be traveling from a dense to a rare medium, meaning from one of a particular refractive index to another of a lower refractive index. And secondly, that the angle of incidence must be greater than the critical angle. Now, we are going to apply Snell's law at the critical angle. So, if we recall Snell's law, eta 1 sine theta 1 is equal to eta 2 sine theta 2. Now in this case, eta 1, representing the angle of incidence, is the critical angle, as shown here. Whereas eta 2, which is the angle of refraction, is 90 degrees. But sine 90 degrees is 1. So we simply have eta 1 sine c is equal to eta 2. Or if we arrange this a bit, we get sine c is equal to eta 2 divided by eta 1. So the ratio of refractive index of medium 2 to that of medium 1. In many cases, we could have the particular situation that medium 2 is air. That is, for example, we have a light ray traveling from glass towards air, from water towards air. So if this is the refractive index of medium 2 being air, then it is 1. And therefore, we get simply sine c is equal to 1 all over eta 1. And here we have a natural phenomenon caused by total internal reflection called mirage. Basically, it makes hot surfaces, such as hot roads, appear wet, as shown in this photo here. It may also lead to fake visions of water in the desert, for instance, which is obviously a very dangerous thing. Now let's see why this happens and how it is related to total internal reflection. If we imagine a light ray approaching a hot surface, it will encounter layers of air that become warmer and less dense the closer it is to the surface. So as the light ray travels towards the surface, it is gradually deviated away from the normal, as shown by this diagram here. So we have the light ray approaches, and at each layer it bends away from the normal. And this happens since it is constantly traveling from a dense to a less dense layer of air. The angle of approach, in other words, the angle of incidence, is hence gradually increasing, and eventually what happens? It exceeds the critical angle, thus causing total internal reflection. To our eyes, what appears to be a puddle of water is simply a reflection of the sky. Total internal reflection may also be demonstrated with glass prisms. Here, I'm showing a right-angled prism oriented in two different ways. The first one on the left will cause the light ray to be deviated by 90 degrees. Note that the light ray enters the prism at normal incidence, meaning along the normal. The angle of incidence is thus 0 degrees and not 90 degrees, as some of you might be thinking, since the angle is measured with the normal. The angle of refraction is hence 0 as well, such that the light ray enters the prism undeviated. Thus, it approaches this face at an angle of incidence of 45 degrees. But the critical angle at a glass-to-air boundary is approximately 42 degrees, as shown here. So, we saw that the sine of the critical angle is equal to the reciprocal of the refractive index. So the critical angle is inverse sine of 1 on 1.5. And we get 41.8 degrees, which is approximately 42 degrees. So since the light ray is approaching this boundary at an angle of incidence of 45 degrees, which is greater than the critical angle, then total internal reflection occurs. And that is why it undergoes a deviation of 90 degrees. The diagram on the right shows the prism oriented such that the light ray undergoes a deviation of 180 degrees. And this happens because total internal reflection occurs twice, at this point as well as here. You must be aware, though, that prisms might not always be right-angled, such as the one given in this question. Hence, you must be very careful when completing the path traveled by the light ray through and out of the prism. And this must be determined through relevant calculations, and not by reproducing from memory some diagram you've seen before. Let's go through this example together. Let us now consider a ray of white light incident on a glass prism. Light is observed to split into its constituent colors, a phenomenon known as dispersion. But why does this happen? We have already said that as light enters an optically denser medium, such as glass, it is slowed down and is hence deviated, a phenomenon that is known as refraction. Now, you must also recall that white light consists of all the colors in the visible part of the electromagnetic spectrum, from violet to red. So, what happens is that in glass, each color will have a different speed, which leads to a different angle of refraction. And thus, each color will take a different path, which explains why colors are seen separately through a prism. Red is found to be the least slowed down, and is hence the least deviated. On the other hand, violet is the most slowed down and thus undergoes the largest deviation. You must also recall that the ratio of the speed of light in air to its speed in glass is called the absolute refractive index of glass. But now we're saying that in glass, the speed of light for violet is less than that for red. Hence, it turns out that the refractive index of glass for violet is greater than its refractive index for red. So, in other words, we're saying that the refractive index of a medium depends on the wavelength, which means the color of light. In fact, when we say that the refractive index of glass is 1.5, we are just indicating an average value, because we find that the refractive index of glass for violet is about 1.53, whereas that for red is around 1.50.